Hello, I am Bardia Konh, and I am presenting dynamic characteristics analysis and FEM modeling of flexible joints of an activated flexible multi-joint needle. This slide shows a little background about needle insertion methods. Needle insertion has been used in many therapeutic and diagnostic procedures. It has been used for biopsy to diagnose the cancer via biopsy samples. It has been used in brachytherapy and thermal ablation to kill the cancer locally. The purpose of needle insertion procedures has been to reach the target more accurately, and also in many cases surgeons need to follow a trajectory, desired trajectory to reach the target. There has been a lot of research about bevel tip needles, and bevel tip needles are working by the interactive forces from the tissue that is applied to the bevel tip in order to curve the needle, reach the target. And basically the input parameters to guide and control the needle inside the tissue are insertion and rotation of the needle base. So one problem with bevel tip flexible needles is that the operator or the robot has only control on the base of the needle by applying insertion, rotation, and also insertion speed. The other problem with this system is the system is under actuated, so the number of actuators is actually less than the state of the system. And one of the good methods that's been used in order to control this type of needle is model-based control. And one of the good models to see the dynamics of the needle insertion is known as non-holomonic control, which needs the needle to be inserted. It needs an insertion depth in order to curve, in order to reach different points. So there has been a limitation or reachability points of the needle. In order to address those limitations, we have introduced an active needle that is actuated by shape memory alloys, can reach different size reachability with higher reachability and control for the operators or for the robot. This slide shows a recent design of the 3D steerable active needle. It is 3D printed. The shape memory alloys are inserted inside the needle so that it doesn't touch the tissue to prevent thermal damage. It actually has 3 wires distributed on the needle in order to give the needle 3D steerability. We have tested the needle in air, and we have actually developed a control strategy in order to control these 3 actuators in order to reach any points that we want in the space. We have this paper that is recently accepted for publication, and it shows a relationship between electrical resistance and deflection of the needle, and we use that for control. So as can be in this slide, we were able to follow a vertical line with reasonable accuracy. One important component of our active needle was the flexible joints, and that's the purpose of this study that I'm presenting here. So the flexible points play an important role for the kinematic model of this needle. As can be in this picture, the high deflection of this flexible joint, which is under actuation of shape memory alloys, plays an important role in kinematics. So this paper represents the flexible joint as nonlinear springs. So for characterizing the nonlinear springs, we applied certain force to the flexible joint in order to see how it deflects. To calculate the deflection of the flexible joint, we measured the forces applied by shape memory alloys to this flexible joint. This graph shows the measurement on this force. We applied this force in finite element analysis while we are modeling the flexible joint material by nonlinear plastic, and then we calculated how much deflection this part will actually get. We measured the deflection by experimental methods, and we saw that there is a good agreement between the prediction and actual experiment. We are hoping to use this characteristic in our dynamic models in order to make even more accurate control of the system. This concludes the presentation. Thank you for your attention.